So let's go ahead and get started on this section, 2.4. This is going to be an introduction to paths and curves. Okay, so you can see from the drawing here, we have some kind of curves living in space. And so we're going to talk about this. So let's remember this idea, this concept of parametric lines. So we talked about this in chapter 1 stuff. So it's like week 1, we were talking about these equations for lines. Like for example, we had equations of like the form L of t equals, and the equations were ordered pairs or ordered triples, and you get something like 2 minus 3t, 4 plus t, and then let's say 1 plus 2t or something like that, right? And this, an equation like this was an equation for a line, right? But the point was that you had a function, you had your three variables, x, y, and z, were functions of t. So this is like x of t, y of t, and z of t, right? And so this was how we talked about lines, but you can notice that x, y, and z always had a certain form to them, right? It was always some constant plus some other constant times t, right? So it's a constant term and then a linear term in t, right? It's constant and linear. So this was kind of like each of these little equations looked like the equation for a line like y equals mx plus b, but instead of x, it was t, and it was 3 different components. And so each of them was kind of following this like what we'd call linear pattern. And so what we're going to see today is I'm going to say, okay, well, we can do this sort of concept with any old equations here. We don't have to necessarily use equations here. We're going to start studying functions that look like that, okay? So that's what we have going on here. Okay, this is just kind of a review. Remember, parametric lines are this idea of each, you have x, y, and z, and each of those things depends on t. So in general, you'd say that the L here is a function from R to R3, right? So someone in my office hours last week was asking about this notation, right? And so I wanted to highlight it here, right? So the input is you have 1 variable and the output is 3 variables here. And so this would be, you'd call this single variable, or vector valued single variable function, right? And so this is kind of how you can tell that this is going to be a path, right? In general, or a curve, and we'll see the formal definition in a second. But these, specifically the ones we've seen so far, have been lines where we have equations in this form in each variable. Okay, so let's look at the definition of a path or a curve. We'll see. So paths and curves. So a path is a map from an interval, right? So A to B is just like, this is here, right? Shorthand notation for T, your input is going to be between A and B, right? Less than it, it's bigger than or equal to A, but it's smaller than or equal to T. That's what this means. In particular, this is a subset of R1, or just R, right? This is a subset of the real numbers, right? So you can think of it as this would be a vector valued, right? Because the output can be vectors. I guess it might be a scalar valued, but it's probably vector valued. And it's single variable, right? Because you only have 1 input, right? Because this is a subset of the real numbers. Okay, we just typically think of it as having a start. Is it starting and ending along a certain interval, right? We just go along a certain interval. Okay, and we call so like this is a fancy definition here. Oh, I forgot to highlight a certain word. So this, the collection of points is called a curve, right? So there's a subtlety here. The path is what we call this map, right? But the actual drawing itself, the actual drawing of that the path makes, is called a curve. Okay, so there's a subtlety. You can think of paths and curves as almost being synonyms, but there's a subtle difference. So basically what's happening is we live, so we have like the real line living out here somewhere. I might even do something like this. Okay, and then you have, a certain interval. So that's A, that's B. Then we have the interval between A and B, like that. Okay, and then we have a map which sends us from here to maybe your two-dimensional space over here. It could be 2, 3, n dimensional, but for this drawing, I'll use 2 dimensions. Okay. And this path is the thing. This here is the map which sends us from here to here. This is the thing we call the path. And that path will draw some kind of picture when we're over here, right? So you plug in A, that puts us somewhere, let's say here. Okay, and then it follows some kind of path and it ends up somewhere over here. So these endpoints over here, this endpoint over here is C of A, and then this over here is C of B. I mean, it does. I mean, the path can go in the opposite direction, and we'll see some of that in kind of like how you can kind of tell what direction it's going in later. But you can just kind of think, okay, we have the interval. The path is what maps that interval into some higher dimensional space, and then the curve is the sort of drawing it makes in that space. So if you just look at that drawing, we call that the curve, and the curve has some endpoints here, which are just the points that you get from plugging in A and B, the endpoints of your interval. Okay, cool. So we're gonna see, so like we have other ways of writing equations for curves, right? Like if you have like a circle, certain special equations, like a circle is like, you know, you can talk about that in terms of just x's and y's. And so sometimes we're gonna talk about in a little bit why it's important to add this, or why it's interesting to add this extra parameter t, why it's interesting to introduce this t, when sometimes we already have names for these curves or other equations for these curves. So let's see some examples of paths. So let's look over here. So let's start with this first example here. We're going to sketch the following paths. C of t is equal to t comma t squared. So you can see here, this is a function from r, because it has one input, not r. It's from some interval to R2, right? There's two outputs and it has one input. So you might think, oh, it should have been R. But this here, right, the fact that t goes from 0 to 2 tells us that we're not going along all of the real numbers. We're not plugging in all real numbers. We're just starting at 0 and stopping at 2. We're just going to put those, and we're only going to plug in those numbers. Okay. Now I'm starting with this like sketching problem. Okay, we're going to learn about different types of problems that you can talk about in different ways you can analyze these paths. So you're not necessarily going to have to sketch things on quizzes and stuff, but it's important to kind of have the skill of, okay, how would I sketch this by hand if I absolutely had to? That being said, Desmos, GeoGebra, I think they can handle parametric paths like this. So if you plug this into GeoGebra, it would give you some kind of picture. I think the hardest part might be just restricting it from t goes from 0 to 2, but there are ways to do that in Desmos. So you can definitely use your graphing calculators as tools, but let's see how we would do it by hand, okay? Just so that we could kind of get the idea of what is actually going on when you graph something like this, okay? So what we're going to do is we're going to use this parameter and we're going to feed it these inputs and we're going to see what the outputs are. So we're going to plug in a t, it's going to give us an x, and it's going to give us a y. Okay. So Going to make a little table, just like when you were first learning graphing of functions, right? The most foolproof way to graph a function is to brute force, just plug in, make a little table, plug in values of x and see what the outputs are. I say brute force, but that's just kind of the most, how do I say this? The most like guaranteed way to actually make sure that you get some kind of answer, right? In general, when we actually learn how to graph things, maybe we'll use a table the first time, but then we like learn tricks for graphing special kinds of functions. And I think that this is no exception. It's just sometimes the functions get kind of weird. And so it's best to just kind of fall back on making a table. So we're going to plug in numbers from 0 to 2. Okay. Let's start with, 0. That's a good place to start. The endpoints are always good. So we plug in 0. Then the x value is just whatever t is. So x is just t. And then y is t squared. So we plug in t equals 0 and we get another 0 there. Okay, so at t equals 0, that was not hard. Okay, I'm just going to go up to the next whole number. And so we get 1. What happens when we plug in t equals 1? Again, x is just t in this case. This is kind of a simple example. So x is just 1. And now y is t squared. And so we get another 1. Okay. Last, we're going to plug in t equals 2, right? Because this goes from 0 to 2. And we get t equals x equals t. So again, x is just equal to 2. And y equals t squared. So we take that 2 and we square it. So we get 4. Okay. So we get 0, 0, 1, 1, 2, 4. Okay. And now what do we do with this? With this table? Well, we treat the x and y's as ordered pairs, right? So I'm gonna set up a coordinate grid here. Okay. Okay. And we're gonna start sketching some of this. So at t equals 0, we have something like, we have 0, 0, right? This is t equals 0. T equals 0, you're at the origin. Then at t equals 1, we're at 1, 1, where x equals 1, y equals 1. So that's t equals 1. And then at t equals 2, we're at 2, 1, 2, 3, 4. T equals 4. Now in this case, ultimately, when you're doing this, if you don't have some other trick for graphing this, you're going to say, okay, we're going to plug in a few points, see if we can connect the dots easily. If there's not enough information, then we'll add a few more points in between. Oh yeah, that should be t equals 2. But yeah, so basically if there wasn't enough information here, we can do t equals 2. But maybe from here, can anyone tell like what sort of shape this is making? What shape is this making? You can also kind of figure it out based on the equation over here. So this is like a parabola, right? Because we go from 0, right? So it's going to give us like this shape right here. Okay. And you could plug in some points in between to kind of give you a little more information. So you could plug in t equals 1/2 and see kind of just have that extra information. In this case, you also, like I said, you have, right? So you have here, you have y equals t squared and x equals t. So you can kind of see that there's some implicit relationship between x and y. So y equals x squared, right? Which is why we get a parabola. In general, it's not always going to be easy to just do some sort of plug-in play here, where you can just kind of swap it and get rid of the t altogether. And the t does actually give some extra information that we'll talk about, I think, on the next slide. But this is kind of a nice helpful way in this case that we were able to see, okay, yeah, no, y equals x squared. So we're just t goes from 0 to 2. So in other words, x goes from 0 to 2, and we're just doing y equals x squared. Someone's asking what will the graph look like if, so if we drop this or equal to. So for paths specifically, we always want to have the or equal to, but if it didn't, I guess you would draw like open circles here, right? So sometimes we use open circles to represent like we're not including that point, right? So it draw an open circle there. It would still be mostly the same, except you wouldn't include the endpoints. But yeah, for paths, we usually include the endpoints. I don't think we would ever not include the endpoints. Okay. Okay, cool. So now let's do similar process, but for this function over here. So we're gonna have t, and we're gonna have our x and our y. Okay. Okay. So t again is going from 0 to 2. It doesn't have to go from 0 to 2. Obviously, it can go from 1 to 3, or -1 to 27, whatever, right? 0 to pi. Sometimes if you see like sines and cosines, they'll have some stuff about pi over here. Okay, cool. So let's start at 0 again. I'm gonna give myself more room this time. I have a feeling I'm gonna have to plug in more points. Okay, so we plug in t equals 0. In that case, when I plug in t equals 0 for x here, I get 2 to the 0, which is 1. Okay. And then I get sine of pi times 0, which is sine of 0, which is 0. Okay. Now I'm going to leave myself some space because I have a feeling I'm going to have to come back. And I'm going to go to t equals 1. Okay. And if I plug in t equals 1, my x value is 2 to the 1, which is 2. And my y value is sine of pi, which is, again, 0. Okay. And then we plug in t equals 2, and then we get 4, and then again we get 0. So far the y has been 0 in these 3 points, which is why we're going to want to plug in points in between. Because if we didn't know better, right? So let's plot what we see so far. Okay, so oops. Okay, let's plot what we see so far. So at t equals 0, we're here. We're at 1, 0. Okay, so this is t equals 0. And then at t equals 2, we're at 2, 0. This is t equals, this is t equals 1. Okay. And then now at t equals 2, we're at 4, 0. And we might be tempted here to say, okay, well, if I were just blindly connecting the dots, it's just kind of a straight line like this, right? But you should see like, okay, there's a sine function here. The sine function oscillates, and just because it's at 0 at these 3 points, we should see that there's definitely not necessarily going to be 0 in between these 2 points. It's not just going to stay at y equals 0 that whole time. So it's probably going to be doing some kind of like oscillating, or but we want to see just have a little bit more information. So let's plug in t equals maybe like 1/2, right? So at t equals 1/2, let me change back to this color. We get something like the square root of 2 here. Okay. And then over here, we finally get something interesting. We get 1, right? Sine of pi over 2, which is 1. Okay. And then over here, I'll probably do 3/2, right? Just 1.5. Okay, just added some halfway points here. So t equals 1.5. This is equal to the square root of 8, right? And you can verify that. Basically, it's 2 cubed to the 1/2, which is the square root of 8. And then we get, again, sine of 3 pi over 2, which, again, if you remember your trig, is -1, right? And we know sine is never going to get bigger than this or smaller than this. So I think this is going to be a good little layout here. It does require you to kind of see, like, okay, well, where's square root of 2? If you remember, square root of 2 is like 1.4 or something or so. Basically, it's less than 1, and it's less than 1.5. So it's somewhere up here. So at t equals 1/2, we're going to be somewhere over here. I should be doing that in blue, right here. This is going to be your t equals 1/2. And t equals 3.5. Your x value is the square root of 8, which is just a little bit less than the square root of 9. And the square root of 9 is 3. So we're going to be not quite at 3. We're going to be slightly before 3 here. So this here is t equals 3/2. And now if we connect these dots, it's kind of more clear what's happening. We're taking our sine curve, but we're kind of stretching it out here. And you can imagine what would happen if, or maybe you can imagine what would happen if we went up to like t equals 4. This would kind of just start stretching out, because these intersections with the x-axis would be happening at further and further apart. They'd be happening at these powers of 2, right? And so at these powers of 2, it's wherever these integers are, these whole numbers. And so like t equals 3, it wouldn't happen again until x equals 8. So it'd be like out here. So it would be stretched out way out here. And if you started plugging in negative numbers to this, it would be kind of like wildly oscillating closer and closer and closer to 0. Okay. Cool. Yeah, so that's kind of how I would go about these sorts of problems, just kind of doing like a plug in and check sort of thing. Again, like I said, if you would like, I think even for a problem, even like this problem here, it would be helpful to check out like a Desmos graph of it, like plug it into Desmos, and then compare what you sketched to what Desmos did, because Desmos is, a computer. It's can make things a lot more precisely than a human can. So, look at it on Desmos, see, okay, what did I get right? Did I get anything wrong? Also, it allows you to tweak the problem slightly and kind of see how that changes the outcome. For example, all of this I've been saying, like, what if we change the endpoints here? What if we threw in some negative numbers? What if we threw in, got this number to be bigger or something like that? What would this function look like? If we're doing this method that I'm showing you here, that means we have to plug in a whole bunch more numbers. But if you're on Desmos, it's just changing one little input. So, maybe try it with one set of numbers and then see what the graph looks like. And then plug it in the Desmos, see kind of what happens if you tweak these numbers here. Okay. Cool. So let's keep talking about this graph. Let's talk about like why we would want to introduce this t parameter. So for example, like over here, like why we just had like y equals x squared from x equals 0 to 2. Why would we bother including this t thing? And so we're going to see kind of what extra information this t gives us, right? Because t, if you hear the letter t, you're thinking, okay, maybe this has something to do with time. So, time is going from 0 to, some number, or it's going along some interval. So what does that mean in terms of the graph? So the way I'm phrasing it is it kind of gives some kind of notion of orientation, or even like you can think of it as direction along the path. That's kind of how I like to think about it. So I wrote it here as orientation. You can say it as like its direction along the path, okay, or the curve. Okay, so let's start. Let's look at this sort of these examples here. So we're going to go through them kind of quickly, but they're related, so it won't be shouldn't be too hard. So this first one here is x squared plus y squared equals 1, which is the equation for a circle. And this is not parametric, so this is not a path in the sense we've been talking about. This is kind of going back to just kind of us remembering like kind of the different graphs for different equations that we learned in like pre-calc, right? So this is a unit circle. So if you remember, that looks, it's the circle of radius 1, x squared plus y squared equals 1, right? And so we get something like this, and it's just this drawing, and that's all we get, right? That's all we get from this. Okay, now let's look at this over here. This is cosine of t, sine of t, okay? And I'm bringing this one up for a couple of reasons. The first reason is like, okay, so we can do this, we can graph this using this method over here, like making a table. And if you didn't know what this graph looked like, that would be a perfectly valid way to do it. But if you remember stuff about your unit circle, you remember that if something is of the form, if the x value is cosine of t and the y value is sine of that same t, basically this is just going around the unit circle, right? And t is representing your angle. You can replace t's with theta here, and you're just saying go around the unit circle, okay? So what this path is doing is it's going around the unit circle. And so the graph of this, because theta goes from, or t goes from 0 to 2 pi, it goes all the way around, it's exactly the same, right? And so we get the exact same picture. Okay, I have the power of copying and pasting, so that makes my life a little easier. But so you might think, okay, so like then what's the point of giving it a different equation? Like, why bother with this? And the point is that first of all, you get a starting and end point, right? So this is t equals 0, and it's also t equals 2 pi, right? So if you plugged in t equals 0, you'd get 1 comma 0, right? And so that's what this is. And same thing if you plug in t equals 2 pi, you'd get this point here. Okay. And what's happening is if you start at t equals 0 and you increase, right? So as t increases, we're going in this direction. So this little symbol here means as t increases, this tells us the direction that we're going. So in this case, this parametric equation tells us that we're going in the counterclockwise direction. Okay, so this is us going counterclockwise. Okay. Now, if we look over here, this equation looks similar, but I've switched the roles of sine and cosine. Now, maybe this is not how we're used to seeing the unit circle, but you notice that if you plug this x and y back into this equation, right, you actually get, this is actually also true. This is also a sine squared plus cosine squared is also equal to 1. So this is also an equation for the unit circle. So all of these are giving you the same curve in two-dimensional space. Oops, that's what I wanted. Okay, but the difference is the orientation. Also different with this one is the starting and ending point. So if I plug in t equals 0, then I get 0 comma 1 instead of 1 comma 0. So I start up here. This is t equals 0. Also t equals 2 pi. And instead of going counterclockwise from here, we're going to go clockwise from here. Oops. So it's something like this here. So this extra parameter of t is giving us more information than we had over here. So if I asked you to just give me an equation for a circle, this is totally fine. But if I said, give me an equation for a circle which starts here and goes counterclockwise, then this is the circle. This is the equation that you want to do, right? Because you need the parameter t is giving you kind of, as time moves forward, as t increases, which direction is the path moving. You can think of this path as it's like telling you like there's a particle in space and it's moving around, and this is keeping track of it. So it's telling you which direction that this path is going. Okay, cool. Okay. Yeah, so this if you see cosine sine, you get a circle. If you see sine cosine, you also get a circle, but you're going in the opposite direction. You're switching the roles of x and y. Okay. So yeah, so you're gonna see there's like some problems on the homework that's like give an equation for a circle which goes clockwise and starting at this point, and so you're gonna have to use a little bit of your trig and then just kind of this notion of kind of which direction these equations go. Cool. If you want to change the radius of your circle, right, you can just throw, if you remember your polar coordinates, you can just throw the radius in front of the sine and cosine. So you could, if this was 2 cosine and 2 sine, it would be a circle of radius 2. Okay. Same thing if you want to make an ellipse, then you just multiply like one of these, or you multiply them by different numbers. So like if you multiplied by 2 and 4, then the x value would be scaled by 2, but the y value would be scaled by 4. So it would be like stretched out more in this direction than it does in this direction. So you'd get an ellipse. There's some examples of that on the homework. Okay, cool. Okay, cool. So let's see next. We're going to have, this is a calculus class after all. So we're going to want to talk about rates of change, which, you might recognize the physics term velocity when talking about rates of change. So, so you have a path. Here I've listed it as going from R to Rn, but remember, it can also just be going from just some interval instead of all of R. Sometimes we write paths as going from all of R. A lot of the equations we've seen so far would work perfectly fine if instead of restricting to a certain interval, t goes from 0 to 2, or t goes from 0 to 2 pi, you can just say t goes from -infinity to infinity, and it just is everything. And the equations would work, but the actual picture of the path would look, the curve would look a little different. And so the velocity of the curve, as you can imagine, is related to the derivative. So here, this notation that we see here, c prime, is the same as the notation you'd use in single variable calculus for just the derivative. And it's going to be given in this case by something we've seen before. Specifically, it's going to be the gradient of c, which, if you don't remember, is the vector given by dc, so it's going to be dc1 with respect to t, and then, this is not the gradient, it's the total derivative, thought of as a vector. And then dc n with respect to t. So it's not the gradient, right? It changes. It's for scalar valued functions in several variables. This is not. It's not that. This is a vector valued function in one variable. And so we're always taking the derivative with respect to t, but we're doing this trick where we break up c of t, right, is equal to, right, c1 of t. You break it up, and it's a vector valued function, but you could break it up into its scalar valued parts, right? So typically, before we were calling this like x of, if it's in 2 or 3 variables, you could call this x of t or y of x of t, y of t, z of t. That's very a common way to do it. But you can also just break it up into its parts if there's more variables. Okay. And yeah, so if you remember the total derivative, it should be a matrix, right? But if you work out the matrix of partial derivatives for this function, you end up with a column, just a matrix that is just one column and a bunch of rows. And so we sometimes call that a column vector. And so if you just think of that column vector as a vector, you get exactly this, right? And so you'd usually write these, on top of each other in terms of this matrix here. Okay. Cool. So the important thing is that if you want to take the derivative, the velocity of this, you take this vector here. So geometrically, C of t, C of t naught, or C prime of t naught, is the vector tangent to C at C of t naught. So you kind of have this path. So if you remember the cover of this, the cover page for this these notes, you have some path and you're kind of just going along, and you're doing whatever. Okay. And then at some point, let's say here, we have T naught. This I guess should be C of T naught, right? You plug in T naught, this gives us, this is where we end up, and then and you get a vector kind of tangent to it. It's kind of shooting off like this. And this vector here is C prime of T naught. Okay. So if you've taken a little bit of physics, right, then you maybe know that velocity is like it's related to speed, but it has direction, right? So going 10 miles per hour in this direction is different from going 10 miles per hour in this direction. So that's two different velocities, right? Because they have direction. And so what this vector is doing is it's saying, imagine earlier I mentioned that paths you can think of as it's a particle moving through 2 or 3 dimensional space or some higher dimensional space. And so you have, imagine you're moving this particle, right? What this is doing is it's saying, this is pointing in this vector is like saying, okay, this is where the velocity for the vector is. And so it's moving as kind of as the particle moves, it's kind of pointing wherever the whatever direction the particle is going. Okay. Cool. So let's do some examples. So to start, we'll just do like some computational examples. Let's just compute some of these. But then we'll see kind of what we can do with this extra information. So to start, let's just compute the velocity of this. So this is what I was talking about before. This just looks like, we can do this problem here without knowing what this shape looks like. But just for your information, this is going to be an ellipse, because basically it's the same circle, the equation for a circle, you have the cosine and sine, but you're stretching the x and you're stretching the y by different amounts. And so you're stretching the x by 7 and the y by 6. And so you're stretching more in this direction than you are in this direction. And so you end up with an ellipse that's slightly wider than it is tall. Okay, so just kind of for your information, you're kind of going around this elliptical shape. That's what this particle is doing. It's in two dimensions, just going around this big elliptical shape. Okay, and so if we compute the C prime here, all we're doing is we're computing. I wrote it as a vector up here, but you can also write it as just like a point here. That's kind of what I'm doing here. So. Actually, maybe I'll write it as a vector. Remember, in my notes, I can be kind of picky about like when I use parentheses or the square brackets when I'm talking about a point or a vector. But as you've seen in the homework, it doesn't care. It doesn't usually. You could just use parentheses all the time, and it'll be totally fine. So here we're just going to take the derivatives of each of these parts one at a time. So this is -7 sine of t. And then this is 6 cosine of t. Okay. So maybe for this first example, I'll do a quick sketch of kind of what's going on. So if we have, I mentioned that the graph of this thing is just kind of a big ellipse, and I won't draw this necessarily to scale, but you have something like, we start over here and we kind of do something like this, okay? So it's something like this. It's wider than it is tall. And then we see, okay, if we compute at t equals 0, we're here, right? So this is at t equals 0. T equals 0 puts us at this point here. Okay. But the important thing that we care about with C prime is what is this? What if we think of this as a vector based at this point? What does it look like? Well, if at t equals 0, this is so C prime at 0 is going to be sine of 0, -7 times sine of 0, so 0, and then 6 times cosine of t, which is 6 here. And so the velocity vector here is actually going to go straight up, and the length of it is going to be exactly the height of this here. So this is kind of happening here. And what's going to happen, and we could be here all day and we can say, okay, what happens at like pi over 4? And we look at pi over 4, you're gonna get some kind of, at t equals pi over 4, you're gonna get some kind of vector that goes kind of in this direction or something like that. I haven't worked out the actual details, so I don't know exactly how long it'll be or whatever, but you can kind of plug in some stuff and kind of see what you get. Okay. Cool. So computationally, I don't think these are too bad, especially, if you're just like compute C prime of t, okay, I can do that. That's just, practicing some derivatives. Okay, so 2e to the t, the derivative of that is 2e to the t. E to the t, 1 over t, I should say. The derivative of 1 over t is -1 over t squared, right? You just rewrite this as t to the -1 and then do a power rule. So -t to the -2, which is another way of writing this. And then we just have a polynomial. We could just write that as 2t plus 1. That's the derivative there. Okay, cool. We have our velocity there. That just tells us the velocity as a function of time. Cool. Any questions on that? I think computationally, nothing crazy, right? We're not doing anything. We're not doing rocket science, though. I guess if you were doing rocket science, just some of these computations might be involved. But yeah, this is the computation so far pretty easy. So let's, again, I always come back to the analogy of single variable calculus. In single variable calculus, you learned how to take a derivative, and then you learned about the tangent line. And earlier we learned about a different notion, a different analogy for that, which was the tangent plane. But now we have these paths moving through space, and we're going to learn a different notion of tangent line, like an actual tangent line. So last time when we learned about the tangent plane, we were learning from R2 to R. Now we have R to Rn, so we can just have some arbitrary path. The tangent line will, if you remember your parametric equation for the line, then this actually won't come as too much of a surprise. But, right, so let's draw a quick picture. So again, we have, let's see, you have a path, and then you have a point along the path. And it kind of goes, the tangent line, the tangent vector kind of shows you the direction, and then the tangent line kind of comes in, and this is not the best tangent vector, but the tangent line kind of comes in and, oops, does something like this, right? And so the tangent vector is kind of giving you the direction of the tangent line. And so if you remember how to cook up the equation for a line, right? Well, we have a point on that line. This point here is going to be on that line. And then you have the direction. It's given by the velocity vector that we just talked about. And so the equation for this is going to be C at T naught. So the tangent line of C, I should have said here, at T naught is the point plus the derivative at that point times t, right? Because remember, this is the point you're going through, and this is the direction vector, and so this becomes your equation for the line. Okay, right? So it's pretty. If you internalized how we found parametric equations for the line, and you understand geometrically what this means and what the velocity vector does, right, based on my drawings up here and here, then this shouldn't be too much of a stretch, right? You have a point on along your path, and that's going to be where the tangent line lives. It's going to hit that point. So you have a point on your tangent line, and then you have the velocity here too. This line actually represents something physically too with this parameter. So you can kind of think, and there's some word problems like this on the homework, and I'm probably going to throw one on next week's worksheet because it's a fun problem. But you can imagine that these what's happening is, so imagine you're spinning like something over your head or in a circle. Okay, that circular path you can model with some kind of parametric equation for a path. And what you can say is, if at some point you let go, then it's just going to follow a straight line in wherever the velocity vector was at that point. Okay, so what we can say is, we can say, okay, we're spinning this over our head at this velocity, or and it's following this equation as it spins. Okay, if we let go at t equals this, okay, and we say 2 seconds later, where is it going to be? Okay, and that's what this is telling you here. They're saying t seconds later, this is the position of where that particle is going to be if it just keeps going in a perfectly straight line once we let go. Okay. Oop. So that's kind of what's going on here. This is, imagine like you have a roller coaster, but then at this point it just like stops following the tracks and it just keeps going straight. Okay. Now in real life, there's like other forces, there's like gravity and stuff, so it's not going to completely follow a straight line, but it's like, imagine you're in a vacuum, all the extra conditions that you throw on physics problem. You can ignore air friction and all of that, and gravity and everything. So it's just more realistically, it's like you have a particle that's going around in a circle, and then you just let it go straight, and then it keeps going in a vacuum or whatever. Okay, so let's see an example of computing a tangent line. So this here is an equation here, and this is some path in three-dimensional space. If you stare at it long enough, it might be familiar to you from last week's quiz worksheet, I think, or a worksheet we've done. It's this. It's a spiral that kind of goes up as you kind of move along. So it was in the when we learned about cylindrical coordinates, right? In cylindrical coordinates, this is we talked about this. But if this is not in cylindrical coordinates, this is just in regular Cartesian, and you have as t increases, z is just going up, and on the xy you're kind of forming this circle, and so you're kind of forming this circle as you move up, and so you end up with this. We call it, the fancy word for it is a helix, but we can just call it a spiral going upward. Okay. Again, for a lot of these problems, if it's not asking you to draw it, you don't necessarily need to know what this picture looks like. Okay, but sometimes I find it helpful. It's also helpful for like quick sanity checks. Like if you're like, does my answer make sense? If you're like asking yourself that, then this is like having a picture in your head of what the graph looks like is a good way to get past that. Okay, so we want an equation for the line tangent to this point. So we have c of t. Let's compute c prime of t. That's like the first step. So there's not the order in which you do the steps is not always in this case is not super crucial. So here let's compute the derivative. There's a chain rule involved, so we get negative 2 pi sine of 2 pi t. The negative is coming from the derivative of cosine, and the 2 pi is coming from the derivative of the 2 pi t. Okay. And then over here we get something similar, but no negative, so 2 pi cosine of 2 pi t. And then in the z direction, you always just get this one here. Okay. So this is our c of t and our c prime of t. So this is our position and our velocity. And now we want to look specifically at c of t sub 0. So c of 1/4 is equal to cosine of 2 pi over 4, sine of 2 pi over 4, 2 pi over 4. And then 1/4. Okay. So cosine of 2 pi over 4, that's cosine of pi over 2. So that's 0. And then sine of pi over 2 is 1. And then the 1/4 doesn't go anywhere. Now we can do the c prime over here, c prime of 1/4. So we now have negative 2 pi sine of 2 pi over 4. 2 pi times cosine of 2 pi over 4. And just 1. This 1, again, remember, is coming from here. This z coordinate in the derivative doesn't depend on t at all. So we don't have to plug anything in there. And so now here, again, we just get this. We get negative 2 pi because sine of pi over 2 is just 1. Cosine of pi over 2 is 0. So we get 0 there and then 1. Okay. Okay. So this is all of the information we need. We just need these 3 pieces of information. Sometimes we'll do these 2 in a different order. In order to do this last one here, you need to have done the derivative at some point. So this has to come before this. But besides that, the order of these 2 isn't crucial. I just like to have these 2 pieces of information close to each other, which is not necessary, but it's helpful. So the equation for the tangent line will be c of 1/4, so 0, 1, 4, plus t times c prime at 1/4. Okay, this is totally valid. I usually like to see like the x, y, z in its like kind of final form. So here you'd get negative 2 pi t, 1 plus 0t, I guess, but we won't write that, and then 4 plus t. Oh, this should be 1/4, not 4. 1/4. Same. 1/4. Okay. Cool. So this is kind of a line that lives in 3D space. So this would be another fun one to maybe graph on GeoGebra here. Graph the original curve here, and then graph the tangent, this tangent line here, and see what you get. See how these are related. Okay, cool. So that's it for this section. We're a few minutes early. Someone asked at the beginning of class if we could talk about examples from 2.3. Okay, cool. So here we are in 2.3. Is there specific examples to that person? Are there specific examples you'd like to see from 2.3? Okay. Anything, something from like the homework or something? Anyone? So matrix of partial derivatives and gradients. Okay, yeah, so gradients. So here, let's see. So let's do an example here. So matrix of partial derivatives is basically just our way of putting all possible partial derivatives here. So I'm actually going to probably just make one up here. So maybe I'll do, so find df when f of xy equals x squared plus y squared, x minus y, and xy. Okay. So remember the matrix of partial derivatives is going to be every possible partial derivative you can take. So basically we break this up. This here is f1 of x comma y. This here is f2 of x comma y. And this here is f3 of x comma y. And so we're going to take, this is going to be, let's see, this is going to be a 3x2 matrix, because this is going to be df1 of x, df1 of y, df2 of x, df2 of y. There's an f missing up here, and then df3 with respect to x, and df3 with respect to y. So there's going to be the number of rows is the number of outputs, and the number of columns is the number of inputs. So in this case, it's just x and y. So let's go ahead and do this. So let's start with the derivative of f1 with respect to x is 2x. So I'm going to draw a nice big, so we have 2x. The derivative of f1 with respect to y is 2y. The derivative of x2 with respect to x is 1. The derivative of y with respect of f2 with respect to y is -1. f3 with respect to x is y. f3 with respect to y is x. We have that. Okay. Any questions on this? Let me see if there are other types of homework or other problems about that in the homework. No, it's mostly just computing them. So yeah, so basically if you want to compute a certain entry, you just say, okay, this is in the first row, so I'm dealing with the first coordinate, and it's in the first column, so I'm going to deal with the first input. In this case, that's x. Okay. And so then like if we were down here, this is the second row, second column. So that's second input, second output. Okay. Now, if f is scalar valued, like something like f of x, y, z equals x squared plus y squared z plus z squared, then we call then df, we write df as a vector and call it the gradient of f. Okay, so the gradient is just in the special case of the total derivative or matrix of partial derivatives. And that's in the special case when it has only one output or it's scalar valued, then we just write this matrix, which will just be a row matrix, as a vector. And so df, right, is going to be, so let's just write it as a matrix first. I think I've been using these square brackets when we talk about matrices, so I should stick to that. All of these. Yeah, sometimes when people talk about matrices, they use the big parentheses too. So that's what I was doing there, but I'll stick to what we know. So this should be, according to this should just be df, dx, df, dy, df, dz. So here we have 2x and then 2yz. Again, I'm just taking the partials of this whole thing. And then with respect to z, we have this, only two of these terms depend on z. So we have y squared plus 2z. Okay, and this is me thinking of this as a matrix, right? We have these three, there's three columns, but only one row. But anytime you have only one row or only one column, then we can say, oh, well, that's just basically a vector if we just throw some commas and change the notation, right? So we can think of these same exact partial derivatives as a vector, and we call that the gradient. Okay. Okay. So just to summarize again, the anytime you have a multivariable function, so whether there's several variables as input or it's vector valued and there's a lot of outputs, then there's a lot of possible derivatives you can take. You can take partial derivatives with respect to every variable, and you can take the partial derivatives of every possible output. And so in order to put all of that information in one place, we use this matrix notation. And we'll see actually tomorrow how we can use matrix multiplication along with this matrix of partial derivatives to actually like come up with some kind of chain rule, and we'll see what that is tomorrow. But we're going to use this matrix of partials tomorrow in a more precise way, and so that should be interesting.